Swayam Prabha. Digital India. Educated India.
So, last class I have discussed about various soil exploration processes, and then previous week also I have discussed different in situ tests to determine the soil properties. Now, this class I will start the shallow foundation bearing capacity or the bearing capacity of the shallow foundation, and then I will discuss about the settlement, and then finally I will discuss about the design of the shallow foundation. Now, generally the foundation can be divided into two parts, shallow foundation and the deep foundation. So, shallow foundation is, we can say it is a shallow foundation when the depth of the footing or the foundation is less than equal to width of the foundation. So, this is the width B and this is the depth of the foundation. Now, deep foundation one can say moderately deep if the depth is 15 times and the less of the width, and if it is more than 15 times of the width, then it is called deep foundation. So, shallow foundation can be different types. It can be strip footing on the continuous footing. Strip footing means where the length is much larger than the B for a retaining wall. So, this is the retaining wall where the length is much larger than the B. That type of foundation is called the strip foundation or continuous foundation. So, it can be for load bearing wall. It provide for a row of columns which are closely spaced and that their footings overlap each other. Sometimes if the your columns are very closely spaced, so that their footing will overlap each other, then we can provide a combined footing whose length will be very much larger than the width of the footing. Then you have a spread footing or isolated footing. Isolated footing means here one footing will be placed below one individual column. So, that can be square, that can be circular, that can be rectangular also. So, it can be a combined footing also where two or more columns are very closely spaced, so that their foundation will overlap. So, in such case we provide a combined footing considering these 2 or 3 columns, then that type of footing is called combined footing. And sometimes we provide one single footing for the entire structure, considering all the columns under one single footing. So, that is called the one single foundation. So, that is called the raft foundation. Okay, so, now the choice of particular type of foundation is depends on the how much load is coming, what are the soil properties, then which type of structure we are constructing, and the if we have different specific requirement or not. So, but during the design we have two basic criteria, one is settlement and one is bearing capacity. That means the settlement of the foundation should not be excessive, and the load that is coming on the foundation that and finally it is coming on the soil should not be more than the stress that soil can take. So, before I go to the bearing capacity part, there are different terminology that we should know. That one is called the gross load intensity, that means the total load, that means load that is coming from the superstructure, then the load of the foundation, and then the load of the soil or the field. So, this is Fs. So, load of the field. So, this field soil, this soil or field soil load, the foundation along with the column, this load and the total load which is coming to the column from the superstructure, that means the QC foundation load and the soil load, the total load and divided by the area of the foundation, that is called the gross load intensity. Then ultimate bearing capacity, the maximum gross intensity of load that soil can support is called the ultimate bearing capacity, and net ultimate bearing capacity, that means we have to subtract the surcharge or the soil pressure, that means gamma into dF. So, that gamma into dF if we surcharge, so that is the net amount of pressure that we can apply to the soils, because already the soil surcharge is already there. So, that means the net one that we can apply is gamma dF. dF is the depth of foundation and gamma is the unit weight of the soil. Then the net shape bearing capacity, then if I apply the factor of safety, because when we are doing any design we have to apply the factor of safety. So, then that is called net shape bearing capacity, and this factor of safety is vary from 2.5 to 3. Now, we can apply the factor of safety with the ultimate bearing capacity also. In that case, this will be called the gross shape bearing capacity. Okay. Net shape bearing capacity or net ultimate bearing capacity divided by factor of safety. Now, gross bearing capacity or gross shape bearing capacity, that is divided by this factor of safety. So, that means finally, this gross shape bearing capacity we have to apply the net ultimate bearing capacity divided by the factor of safety plus gamma dF. Okay. So, that means as we can say that directly if I apply the factor of safety with the ultimate load, so that will not be treated as gross shape bearing capacity. Okay. So, the gross bearing capacity actual definition is the net ultimate divided by the factor of safety plus gamma dF. So, that means we do not need to apply the factor of safety below the gamma dF part. Okay. Only you have to apply the factor of safety for the external load that is coming. Okay. So, that you just remember that, I mean the gross shape bearing capacity means the net ultimate divided by the factor of safety plus gamma dF. Okay, because here we are just not applying the factor of safety for the soil surcharge. And then the shape bearing capacity, ultimately a shape bearing capacity or allowable bearing capacity and the allowable bearing capacity, two things. Shape bearing capacity is the in terms of settlement criteria. The previous definitions were in terms of bearing capacity criteria. Now, in terms of settlement criteria, the shape bearing pressure is the maximum net intensity of loading that can allowed on the soil without the settlement exceeding the permissive settlement. That means, that much of load I can apply on the soil, so that there will be not the exceeding excessive settlement of the foundation. So, that means every design you have to put a permissible settlement. So, we can apply that much of load such that the settlement of the foundation should not be more than the permissible foundation settlement. So, remember that in the bearing capacity calculation we are applying the factor of safety, but here this permissible settlement value is given and we have to determine the shape bearing capacity or the bearing pressure with respect to that permissible settlement. So, no need to apply additional factor of safety, because it is in terms of permissible settlement. So, already that safety factor is there. So, that means we have one shape bearing capacity pressure and another in terms of settlement and another in terms of bearing. So, minimum of these two will give us the allowable bearing pressure. That means, how much load we can allow on the foundation. So, that will be the minimum of the load that is satisfying the settlement criteria as well as the bearing capacity criteria. So, that is why the maximum net intensity of load that can be imposed on soil with no possibility of shear failure or possibility of the excess settlement. That means, it is the smaller of the net shape bearing capacity and then the shape bearing pressure. So, I mean it is the smaller of net shape bearing capacity, we will calculate the net shape bearing capacity, That means the net bearing, ultimate bearing capacity divided the factor of safety, and we will calculate the safe bearing capacity in terms of settlement condition. The smaller of these two will give you the allowable bearing pressure. Now, the modes of soil failure, how the soil will fail under foundation. There are three types of shear failure. One is the general shear failure, one is the local shear failure, another is the punching shear failure. Now, general shear failure is occurred mainly for dense sand or stiff clay. Now, when we can say it is a dense sand, when we can say it is a stiff clay, then from this table I can get those values. That means I can get this dense sand if it is 65 to 85 percentage of relative density. From this curve also I can see that it is the df by b for the say shallow foundation. So, for 1, so this range is around 35 to 70. So, in this range there will be local shear failure. So, and the general shear failure will be more than 70. So, here also we can see the general shear failure is dense sand. So, this is 65 to 85. So, more than 70 around. So, from this chart also we can see depending upon the df by b, and these are the different range, and this is the relative density x axis. So, we can say that if the relative density is more than 70%, there will be a general shear failure. If the relative density in between 35 to 70, there will be local shear failure. If it is less than 35%, then there will be punching shear failure. So, we can see that for loose and very loose sand, where less than 35, there will be 35 of the relative density, there will be punching shear failure. So, how we can see what is the characteristics of this general shear failure? Then we will get a well defined failure surface below and outside the footing. Then we will get a bulging at the ground surface adjacent to the foundation, and ultimate load we will get a peak of load settlement plot, and we can easily identify the ultimate load of the foundation. But for the local shear failure, it will occur, as I mentioned, for medium or relatively loose sand, or and medium and relatively soft consistency of clay. Then we will get a well defined failure surface beneath the foundation only, not the outside the foundation. We will get a slight bulging outside the ground surface adjacent to the foundation, and load settlement curve will not give a peak value, and so we will not identify the failure load very easily. So, and we will get the significant compression of the soil just below the foundation. And then for the punching shear failure, so this is also different types of failure. So, surface, this is for different type of cases. As I mentioned, this is the general shear failure, this is the local shear failure, this is the punching shear failure. So, in punching shear failure, this is the poorly defined shear planes, and the soil zone beyond the loaded region will not be significantly affected, or it will be little bit effect will be noticed, and there will be significant penetration of the soil wedge shape soil zone beneath the foundation. So, that means this is the wedge, so there will be significant penetration below the foundation, and ultimate load cannot be clearly recognized. Here also we will not get a definite peak, so ultimate load will not be clearly recognized. So, the first bearing capacity was proposed by the Tazaki. So, this is the advanced foundation engineering part. So, I will not go in detail how this Tazaki's equation is obtained. This is already been discussed in the foundation engineering course. So, here I will discuss what are the additional part, or what is the I can discuss, or I can give you the idea about the additional part or some additional things. Those are not discussed in the foundation engineering course. So, but for the continuation purpose, I will discuss about all the bearing capacity theories in brief, and then I will discuss what are the additional things in this course. So, for this Tazaki's bearing capacity theory is basically valid for strip footing. Okay. So, and it is generally originally developed for the general shear failure mode. So, and load is vertical, it is acting at the center of the footing, and ground surface is perfectly horizontal. So, and it is valid for if the depth of the foundation is equal to or less than the width of the foundation. Now, the shearing resistance of the soil above the foundation base, that is from the base and in between base and the ground surface is neglected, but it is considered as a surcharge which is acting on the base of the footing. And you can see the assumed failure surface is not touching the ground surface, it is extended up to the base of the foundation. So, that means you remember that it is valid for strip footing. Originally it was developed for the strip footing under general shear mode, that means for it is valid for dense sand and the stiff clay. Then it is load is perfectly vertical and there is no eccentricity, it is acting on the center of the foundation only, and the ground surface is horizontal, and it is valid for if the depth of the foundation is less than or equal to width of the foundation. So, this is the ultimately finally this expression is proposed, that is the ultimate load carrying capacity of the foundation is CNC gamma df nq plus half gamma b n gamma, where NC NQ n gamma as the bearing capacity factor can be obtained by these equations. So, here the NC NQ n gamma are the function of phi, friction angle of the soil, and C is the cohesion of the soil, and gamma is the unit weight of the soil, and there are and B is the width of the footing, df is the depth of the foundation, and there are two gamma you can see, one is the gamma in the second term and the gamma in the third term. So, for the second term gamma is the gamma of the soil, unit weight of the soil between ground and the base of the footing, and the second term gamma or the unit weight is the unit weight of the soil below the foundation. Okay. And there is a table also, by this table we can also get the bearing capacity factor NC NQ n gamma corresponding to difference phi value. So, now originally this theory is developed for the general shear failure, but if the for the local shear failure also further modification is suggested. Now, if you want to determine the local shear failure, then you have to reduce the C value cohesion by 2/3 and you have to reduce the phi value by using these equation. So, now what I will do? We will do that we will this is the phi value of the soil, now that I will reduce and I will get a phi m by using these equation. Now, by using the table corresponding to phi m, we will determine the bearing capacity factor, but not for phi. So, that means we for phi m we will determine the bearing capacity of the factor, and that bearing capacity is mentioned here dash, that means C n c dash n q dash n gamma dash and so on. Now, when we can say this is the soil is local shear failure or general shear failure, if the phi value is greater than equal to 36, then it is the general shear failure. If phi value is less than equal to 29 degree, then it is local shear failure. If it is in between that, then this will be a mixed state of general and local shear failure. So, in such case we have to determine the bearing capacity by interpolating the values from general shear to local shear case. So, that I will discuss by one example problem, but this is for sandy soil, now where the cohesion is 0. Now, if the soil is C phi soil, then for cohesive soil also we can identify that if the soft soil, there will be punching shear, is moderately soft or the medium consistency clay, then it will be local shear, and if it is a steep soil, then it will be general shear failure. But if it is a C phi soil, then if the phi value is say less than 29 degrees and so, now there is no possibility there will be a general shear local shear failure, because in such case you have to see the load distribution curve, load versus settlement plot. Now it say that if the failure of soil specimen occurs at a relatively small strain, then there will be general shear failure. That means if the in such case, if from the low stress settlement plot, if we see, or the stress strain plot, if we see that the failure of soil specimen occurs at a relatively small strain within the 5%, then that is general shear failure. And if it is the stress strain curve does not show any peak even up to a 20% strain, then we can say this is a local shear failure. Okay. So, during the problem it will mention whether it is a local shear failure or the general shear failure. So, those things will be mentioned in the problem for C5 soil, but for the sandy soil, by identify the phi value we can judge whether there will be local shear failure or general shear failure, and based on that we have to solve the problem for the sandy soil. Now, later on this equation, which is originally valid for strip footing, is modified for the square, rectangular and circular footing also, and this is the correction or the modification factor. Now, this is the alpha 1 and alpha 2, two factors, and alpha 1 is 1 for the strip footing and half for the alpha 2 is half for the strip footing. Now, square footing, this is alpha 1 is 1.3, alpha 2 is 0.4, circular footing alpha 1 is 1.3, alpha 2 is 0.3, and rectangular footing alpha 1 is 1 plus 0.3 b by L, and alpha 2 is 0.5, 1 minus 0.2 b by L, where b is the width of the foundation, a is the length of the foundation. Okay, so, now this is the case for two extreme conditions, that means when C is equal to 0, another is C phi equal to 0. So, C equal to 0, the first term will be vanish because your C is 0, there will be only second term and third term, and if the C equal to 0, then we can see the ultimate bearing capacity of the soil is function of dF as well as width of the soil. That means, for sandy soil, the ultimate bearing capacity of the soil is function of the depth of the foundation as well as the width of the foundation. But if the phi is equal to 0, then as per the Tazaki's bearing capacity factor, you can see phi equal to 0, this NQ is equal to 1 and N gamma equal to 0. So, third term will be 0. So, in the second term also we will get that alpha 1 CNC and gamma dF. So, ultimate bearing capacity is function of depth, but not the width. So, that means width has very negligible effect on the ultimate bearing capacity if the soil is a cohesive soil. But if you want to calculate the net ultimate, that means Q net ultimate, then this will be alpha 1 CNC plus gamma dF minus gamma dF, because the net ultimate. So, ultimately alpha 1 CNC. So, for net ultimate, it is not also the function of the depth of the foundation. Okay. So, that is important thing for the cohesive soil. Now, we can include the water table effect also, because in original developed equation, water table effect was not incorporated. So, we can include the water table effect also, that is CNC QNQ plus half gamma B N gamma. So, for clay, that because if the soil is clay soil, then net ultimate bearing capacity what for your phi equal to 0. So, Q N Q is only C and C, or there will be a alpha term. So, that means there is no unit weight. So, then how the water table will make an impact on this value, because the water table position may change the cohesion value also, because the effect of the water table, if the soil is submerged, then it reduces the undressed shearing strength of the soil due to softening effect. So, that is why it is always better to determine the strength parameter in the lab under saturated condition. So, that means that will give us the worst condition. So, if we determine the strength parameter under saturated condition, so there we will get the cohesion value that will give such as that the in the field the water soil is under submerged condition. So, that way it will affect the bearing capacity, that means in cohesion value. But if it is the C5 soil or the phi soil, then this water table effect will be in the unit weight of the soil, because we have two unit weight. Now, in the two cases is there, if the water table is above the base of the foundation and another is below the base of the foundation. In the first case, if the water table is above the base of the foundation, then the third gamma will be always the gamma sub or the gamma dash, which is equal to gamma sat minus gamma w. Gamma sat is the saturated unit weight of the soil and gamma w is the unit weight of the water. So, it is always that, but the above the water table, then we can use these expression. That means the if I can say this is gamma or gamma bulk and this is gamma sat, then above the water table you have to use the gamma or gamma bulk and below the water table you have to use the gamma sat. So, that means that this will be the thickness or the depth of the soil layer from the ground surface, water level from the ground surface into the gamma plus the remaining depth of the foundation A into gamma dash or gamma sub. So, this gamma I have to put in the second term, and if your dW water table is at the base of the foundation, that means your d A is equal to 0, then the first term will be gamma bulk or the gamma, but the second unit weight which is in the third term will be gamma sub. And if the groundwater table as the water table as the ground surface, then both the gamma will be gamma sub or gamma dash. So, if the water table is as the ground surface, so that will give us the lowest bearing capacity. If water table is below the base of the footing, then we have to use these equation, and here again the gamma dash is equal to gamma sat minus gamma w. So, I will use this expression for gamma sat, and gamma is the unit weight of the soil above the water table, and this is the gamma sat gamma dash, and this is the equation that is given by which we can determine the bearing capacity by incorporating the water table effect. Now, that if the water table position is below at a distance of B from the base of the foundation, so there is no effect of water table. So, for example, if B, this small b is equal to capital B, that means the width of the foundation, then the QU there is no water table effect. So, that means we have to consider the water table effect up to which the water table position is within the width of the foundation from the base of the footing. So, that means up to which the position of the foundation position of the water table is within the base of within the width of the foundation from the base, then we have to consider the water table effect. Now, if the position of the water table is beyond the width of the foundation from the base, then no need to consider the water table effect. For example, we will consider the water table effect if my B is equal to capital B. So, if it is beyond that, then no need to consider the water table effect. Now, the next bearing capacity equation, that is ultimate bearing capacity equation for proposed by Skempton, and it is valid for clayey soil. Okay, and this equation is valid for any depth, because in the Tarzaki's equation is valid for when df is less than equal to b, but it is applicable for any depth. So, this is the net ultimate bearing capacity Nu, and obviously for phi equal to 0. So, this will be CNC and U is equal to undrained cohesion. So, NC for strip footing I will get by using this equation with a maximum value at 7.57 or 5. That means, for this case NC cannot be greater than 7.5. For square and circular footing, this is the expression, but NC should be limited to 9. And for the rectangular footing, the first expression is valid if df is less than equal to 2.5 times of b, and it is valid for df second term is greater than 2.5 times of the width of the foundation. So, this is the expression for the rectangular footing, but remember that this is applicable only for the clay soil. So, now the next one is the Mehrab bearing capacity equation, and then the Henson, and then the basic, and then our IS code also recommended has recommended bearing capacity equation. So, in the next class I will discuss these 4 bearing capacity equation, that means the Mehrab, Henson, basic and IS code, and what are the differences between them. Those things also I will discuss in the next class, because in Tarzaki's bearing capacity equation you can see that it is valid for only vertical load. No, there is no option to incorporate the inclination of the load in the bearing capacity. It is valid for only if the load is acting on the center. There is no option of incorporate the eccentricity of the loading. Then it is valid for a base which is perfectly horizontal. Now, if the base is tilted, then how we can determine the bearing capacity. So, those things will be discussed in later section of this course, because by using the other bearing capacity theories proposed by other researchers. Thank you.